Okay, now in this, I wouldn't call this unit easier or harder, actually probably more complicated, but shorter unit. This is series part 2. And in this unit we're going to be talking about power series, Taylor series, and Poisson series, and then finally using this to find Lagrange errors, which is kind of torturous, but the first things aren't really that bad. So, the first thing I want to define is what a power series is. So a power series is basically a series that kind of looks like this. And it could be from 1 to infinity, something like that. And it's basically some n, something having n's in it. So it can be n, it can be n plus 2, it can be 2n, it could be n factorial, it doesn't matter. Something doing with n times x to the n. Or it can also be x minus c to the n. This is called a power series, and what you need to know is that in this form, C stands for the point that the series is centered around. If you draw this out, it's hard for me to explain what that means, but basically all you need to know is that in this form, x minus cc is the number that's centered around. So for example, if you wanted a function centered around x equals 2, then it would be x minus 2 to the n. So why do you need to know this? Well, we talked last unit about geometric series and about how to find the sum of a geometric series when it goes to infinity. But in this unit we're going to be talking about what if we have a function that is the infinite sum of a geometric series. Now it's kind of hard to understand, but I'll show you. So let's say right here we have f of x equals, I believe it's 4 over 2 plus x. I want to tell you that this function right here, f of x equals 4 over 2 plus x, this function right here is the function of all of the infinite sums of this geometric series. What is a geometric series, you may be wondering? Well, this is the infinite sum, and the infinite sum of a geometric series is a sub 1 over 1 minus r. These kind of look similar, don't they? So we need to simplify to get into something kind of like this. We want to make this a 1. So we're going to divide this whole thing by 1/2 over 1, or we're going to multiply by 1/2 over 1/2, and you'll get 2 over 1 plus x over 2. And then here we have this as negative, so let's make this minus negative right there. As you can see, we kind of just got it into this form. So what we have is that this right here is the infinite sum of the geometric series. Well, now that we have it in this form, we can say that a sub 1 equals 2, and r equals negative x over 2. So a sub 1 equals 2, r equals negative x over 2. So then, to be able to write a geometric series, going from 0 to infinity, you would just write a sub 1, which is 2, times the negative x over 2 to the n. And that is a geometric series that its infinite sum is represented by this function. Now, looking at this, the reason I knew to write it like that is because I'm starting from 0. And by doing that, that means that this whole thing is going to just be 1 for the first term, which makes sense because we want the first term to be 2, and that would make it 2 times 1. So to do the formula for this is to go from 0 to infinity, make the a sub 1 right here, then put the r inside parentheses and take it to the n. Alright, so now that we got that, and we have written that this is the same thing, to write out the first couple terms, all we have to do is write out the first couple terms. If you put in 0 for here, you would get 2, which makes sense because that is what we found out is going to be the first term. To get the second term, well, it would be negative x over 2 to the 1, so it would be negative x over 2 times 2, which should just be negative x. Then it's going to be squared, so it's going to be x squared over 4 times 2, which is going to be plus x squared over 2 plus dot dot dot. And as you can see, it's going to alternate. An interesting thing, something you're going to want to do, is you're going to want to then simplify these series. And you'll see why pretty soon. But if you ever have the r value as something negative, so let's say you have negative x to the n, realize that this is the same thing as saying negative 1 to the n times x to the n. You can pull out that negative and make it a negative 1 to the n. You're going to want to do this because it makes it a lot easier to understand. So we can then say that this is the same thing as x over 2 to the n times negative 1 to the n. So, actually I'm going to write these the other way around. So, what if the question then went on to say that, and remember that the question gave it to you like this. So you had to find this first, and then the question said, what is the interval of convergence? Well, remember we learned last unit that, I should probably show them before I separated these two. Remember we learned that the interval of convergence is taking whatever, being taken to the end and putting it between negative 1 and 1, so we're going to do the same thing. Negative 1 is less than negative x over 2. Sorry, I probably should have done this before I separated these, but 1. Also both sides by 2, you get negative 2, negative x, 2, divide them by negative 1, flip the signs, and you get negative 2 is less than x, which is less than 2. That's the interval of convergence for this power series. The last thing we're going to be doing is taking the derivative and antiderivative of this series. Now this is why you're going to want to pull out the negatives. You want to have it in the simplest form, which is something like this. You could even take this further and make it something like this. If it's x over 2 to the n, then you could also say that this is x to the n over 2 to the n, and therefore you can pull down the 2 to the n, and then you can get rid of this 2 and say that this is n minus 1. We want to have the x to the n kind of by itself, and the reason is because that makes this really simple. You don't have to do that, or the x minus the center by itself. So now if we want to take the derivative, all we're going to do is we're going to pretend like, think about it like this. Once you're plugging in these numbers in the series, you're going to get, you're going to be plugging in 1, you're going to be plugging in 2. All these n's are just going to turn into numbers. So it's going to be 2 to the 0, which is just going to be 1/2. That's a number, it's not a variable. So you can kind of think of this as pulling out the variable and like having this kind of being like a leading coefficient. So if I want to take the derivative of this, let's say I wanted the derivative of this function, you could do that by doing this. And you take the derivative of this, which would be n times x to the n minus 1, and then multiply that by everything here, so it would be negative 1 to the n all over 2 to the n minus 1, and that would be with the same 0 to infinity. You're also going to have the same interval of convergence when you are doing the derivative or the antiderivative. To get the antiderivative of this, well, it'd be the same kind of thing. You would have to do x to the n plus 1 over n plus 1. So in this case, you would then get that 2 to the n times n. That right there is the antiderivative, and it would be in a series like this. Now, I want to say before I get too far in this that you cannot simply write it in this notation. You can't take the integral of a series. You can't do that. That's not the notation you do. So if this is f of x, and you want to find the power series for f prime of x, then you would first write the power series for f of x and then do the derivative by taking the derivative of the x and pretending like this is just a coefficient. Antiderivative, the same thing. It's really simple. If you want to do f to the x plus 1, you would just plug in x plus 1 into the year. That would, by the way, change your interval of convergence, so you need to redo that. But yeah, that's how you do a power series.